Okay, so now we're going to do problem 15. I'm sorry, we're going to do problem 6 from chapter 15. Okay, problem 6. Problem 6 is about, let's say, a particle with a mass that's 1 times 10 to the negative 20 kilogram is oscillating with simple harmonic motion with a period of 1 times 10 to the negative 5th seconds and the maximum speed of 1 times 10 to the 3rd meter per second. You'll also find the angular frequency, which is the symbol omega, and the maximum displacement of the object, which is of the particle. So the maximum displacement, we call that xm. So how do we do this problem? This is a typical simple harmonic motion. You have the mass, you have the period, and you have the maximum maximum velocity. So if you recall, the period and angular frequency, they are related to each other. So they are related by this. T is equal to 2 pi over omega, or omega is equal to 2 pi over t. So in other words, you can calculate your omega, which is just 2 pi over t, and we just plug in the numbers, and your t is given. So your omega should have the value that's 6.3 times 10 to the 5th, and that's in radians per second. Okay, and then you also find the maximum, maximum amplitude. Since the maximum amplitude of velocity and displacement, they are related, we can actually use this equation, which says that the velocity amplitude is equal to the displacement amplitude and then times the angular frequency. So this is as simple as that. So you have the Vm, you have the xm, and the omega, and we just calculate. So our xn is equal to Vn over omega. And our Vn, we have this value. That's 1 times 10 to the 3rd. Omega, you have this. 6.3 times 10 to the 5th. So once you have that, you have your xm, which is 1.58, and then times 10 to the negative 3 meters. Okay, so this is your xm. So you have the value. That has so you have the amplitude of velocity that has this value, and the displacement has this value. So you can see that this is a simple problem that illustrates how this quantity are related to each other. Okay. So, all right. So the next one that we want to do is problem 13. So let me just erase this. Okay. An oscillator consists of a block of mass that's 0.5, so m is 0.5 kilogram, connected to a spring. When set into oscillation with amplitude that's 35 centimeters, so we can, since it says amplitude, we can just say that the xm is equal to 35 centimeters, and the oscillator repeats its motion every 0.5 seconds. So that we associate that 0.5 to our period. So that's 0.5 seconds. You want to find the period, which actually, is directly taken from the problem. So you want to find the period, the frequency. So you want to find t, you want to find f, frequency, you want to find angular frequency, and then you want to find the spring constant, the little k, and you want to find the maximum speed, so that's your Vm, V sub n, and you want to find the magnitude of maximum force on the block from the spring. Okay, so you want to find the spring force when it's at maximum. Okay, so now we just, as I mentioned, based on the information we're given, we already find that our t value is just 0.5 seconds. And then once you know the period, then it's become very easy to find the frequency, because your frequency would just simply be the inverse of the period. So you have 1 over 0.5, so you get 2. And the units will be in hertz, okay? And then you also find angular velocity, or angular frequency. So angular frequency, you can either use 2 pi over t, or you can use this the following equation, which is just 2 pi times f. So you have the 2 pi and then times 2, and then you want to multiply out the pi. So what you have here is 12.57, and that will be in radians per second. So that's the angular frequency. And then you also find spring constant. So how do we find spring constant? If you recall, when you have when you have an object that's say into the oscillatory motion, and that period only depends on spring constant and also the frequency, the angular frequency. So the equation that you would use is this one: omega is equal to square root of spring constant over the mass of the object. So you also find k, so that's square this and then times your m. That will give you your k value. And then so that's plug in the numbers. Your frequency is 12.57. You square it, and then you times the mass of the block, which is 0.5. So after you do that, your spring constant is equal to 79, and that's newtons per meters. Okay, so that this is what you have, and then you also find the Vm, which is the amplitude, the velocity amplitude. How do we find the speed amplitude? Remember, we had, if you had your xm, your Vm actually, your Vm and xm, they are related to each other. So your Vm is equal to xm and then times omega. So we have our xm, which is 35 seconds. Centimeters, so that's 0.35 meters, and then times your omega. Omega is 12.57. So when you multiply that, you should get your Vm, which is 4.4 meter per second. Okay, so this is the speed amplitude, and then the last thing that you also find is the maximum force that of the spring force. What is the maximum spring force on the block from the spring? So if you remember from the Hooke's law, the spring force is equal to negative kx. So in other words, in order to find the maximum force acting on the block, then you will use the displacement. That will be the displacement amplitude. So you have your Fm. That's equal to you can just drop the negative sign because it is the magnitude that you want to use. And we're plugging out k. The k value that we found was 79. So you have the spring constant, that's 79, and then your xm. So it is xm that we want to use. So your xm is 0.35. So after you do the calculation, you'll find that the maximum spring force acting on the block is 27.7, and that's in newtons. Okay, so that's problem 13. Okay. All right. The next one we want to do is problem 17. So let me draw the diagram first. You have a spring that is attached to a block. So the block has mass m and the spring has spring constant k, and it is given, which is 400. This and then your m. Okay, so let's see. Problem 17. An oscillator consists of a block attached to a spring. Spring constant is 400 newtons per meters. At some time t, the position measured from the system equilibrium location, velocity and acceleration of the block are, so those are instantaneous value, not the maximum value. So you would just use the variable x and not the xm. So your x, at any given, at some point, your x is equal to 0.1 meters, and then your velocity is equal to negative 13.6 meter per second, and then you have your acceleration that's equal to negative 123 meter per second. Okay, so we have the position and velocity and acceleration at some point that have those values. You also find the frequency based on this information. You also find the frequency of the oscillation, and you also find the mass of the block, and you're also asked to find the amplitude of the motion. So the amplitude of the motion then, which means that it is xm, okay, the maximum displacement. Okay, so how do we do this? You have the instantaneous value, but you do not have the amplitude or the displacement. You're given the spring constant. You also find frequency, mass, and this. So what we can do is that if we realize that the acceleration as a function of time and the position as a function of time is actually, they are related to each other. And how are they related to each other? The acceleration is equal to negative omega squared, and then times the position or the displacement. So in that case, we can utilize when x equal to 0.1, and the acceleration corresponding will have that value. So what we have here is that your x is negative 123. And that's equal to negative omega squared, and then your x is 0.1. As you can see, x of t that indicate the position at time t, and so and you have the acceleration that's this value as well. So we can just plug into this. Okay, so this equation, and what we have here is that you have your omega squared that's just simply equal to 120 divided by 0.1. So from this information, you can calculate your omega. And your omega, after you do the calculation, you get 35.07, and that will be in radians per second. Once you have your angular frequency, then it becomes easy to calculate your frequency, because angular frequency and frequency, they are related by this. So you have on the left-hand side, you have this value, and on the right-hand side is the quantity you're asked to find. So your frequency, after you punch in the calculator, your frequency is equal to 5.58, and that's in hertz. Okay? So once you have your frequency and you're asked to find the mass. Now remember, as I mentioned, angular frequency is related to spring constant and also the mass. So what we can use is that omega is equal to square root of k over m. Okay, you can see that this equation shows up again and again. So you can square it. So omega squared is equal to k over m. So you can calculate the mass, which is just k over omega squared. So your k value is 400, and your omega, where's your omega? Your omega is this value. So you can just plug in to that equation. Remember to square it. So after you do the calculation, the mass will be 0.32 kilograms. So this is the mass, 0.32 kilograms. Once you have the mass, and then so we have the mass, we have the frequency, and you also find what is the maximum maximum amplitude. Okay, the maximum amplitude. Let me see. Do we have that? So how do we calculate the maximum amplitude? So let's see, we have all this. So how do we calculate the maximum amplitude? Based on the information here, those are the instantaneous values. So you really can't use them to do anything more to infer what the xm is. So in this case, in order to find the maximum amplitude, we have to utilize the conservation of energy. If you remember, what for a block that's set into the oscillatory motion, you have the energy. There are two kinds of energy present. One is kinetic energy, and one is the spring potential energy. So this energy is your total energy. right? So the total energy of this system will not change because this is an isolated system. So you can calculate based on, so your kinetic energy will just 1/2 mv squared. Your spring potential energy will just be 1/2 kx squared. We have instantaneous x, we have instantaneous velocity, so we can actually calculate what is the energy at that time, and then set it equal to when all the energy has been converted to in the form of the in the form of spring constant. So in the form of spring potential energy. So in other words, you will have at this time t, you will have 1/2 kx squared plus 1/2 mv squared, and that has to be equal to 1/2 k xm squared. This is based on the conservation of energy. On the left-hand side, this is based on at time t, we have the x value, we have the velocity value. Those are instantaneous values, and then the sum of these two energies has to be equal to 1/2 k xm squared. Okay, or that's equal to 1/2 mvm squared. So when you reach the maximum, it can only be in the form of kinetic energy, which is 1/2 mvm squared, or in the form of spring potential energy, which is 1/2 kxm squared. Okay, so we have everything in front of us except xm, which we're asked to find. So let's plug in the numbers. You have 1/2, you have your 400, and you have your x, which is 0.1 squared, plus 1/2 the mass. What is the mass? The mass is mass given. Yes, we calculated. So mass is already calculated. So it's 0.32. And then your V is negative 13.6. You square it. And the whole thing is equal to 1/2 your K value, which is 400, and then your XM squared. So after you punch in the calculator, your XM, you should get a value that is equal to 0.396 meters. Okay? So this is how you calculate, this is how you calculate the maximum displacement. You have to use the conservation of energy because, given the information, the information, we'll not be able to use any other method except the conservation of energy. Okay?